Hello again. Dear participants, now I kindly invite Professor Burak Ekici from Turkey to do presentation. The title of his talk is Formal Categorical Reasoning. Professor Ekici, you are welcome to present your study, please.
All right, thanks a lot. So let me just go ahead and share my screen. Can you monitor my slides in the full screen mode?
Yes, please.
Okay, great. I also want to start with sending my big thanks to organizers for arranging such an interesting event and also providing me with this voice opportunity. My name is Burak Ekici. I'm currently working as an assistant professor at the Computer Engineering Department of TED University here in Ankara. And today I want to quickly exhibit the category theory library that I've been implementing within the proof assistant COC for some time now. Let's take a look into the agenda of the talk point blank. So to start with, I want to spend a few words on the COC proof assistant for those who are just encountering that kind of formal proof environments for the first time. And then I'm planning to carry on with a few discussion on the design principles of the category theory library that I've been developing therein. And at the end of the day, if the time permits, I'm planning to conclude with a case study for exemplification and demonstration purposes. Okay, so what is indeed COC? It is in fact a formal proof management system which embodies a functional programming language alongside a specification language. Of course, in the functional programming language, you can go ahead and implement your terminating recursive functions, and in the specification language, you could state properties of these functions and give them proofs. So it's a two-in-one proof environment system in which you can implement your functions and try also to prove properties of them. So I think the proof assistant COC first appeared as an outcome of the PhD thesis of Professor Thierry Cocon. It was written in 1985 at the École Supérieure de Ulm in Paris. So the mathematical and let's say the philosophical foundations on which the proof assistant COC is based is in fact the Curie-Howard isomorphism, which directly highlights a strict relation, or let's say isomorphism or equivalence in between constructive logic and type theory. So here you can basically take type theory as an alternative to set theory in the sense that it provides some sort of constructive foundations to do mathematics. So according to Curie-Howard isomorphism, any proposition by the constructive logic side can be taken and viewed as a type within the scope of type theory. I mean, a type is just a collection of things that you can inhabit anyways. And in the same lines, of course, any valid proof that makes the proposition hold can be seen as a program of the corresponding type. So this means that indeed the slogan is very obvious here. Slogan becomes really obvious. So you can program proofs just as you program functions. So I think it's a very nice ability to be able to program proofs. Instead of going ahead and writing your proofs on a piece of paper, you could go ahead and implement them within proof assistants like COC, for instance. Of course, this ability to program proofs comes with side benefits. So this way you can certify your proofs, because getting your proofs checked by a mechanical process would be much less error prone in comparison with having a person just checking it out, right? So checking your proofs would be really crucial, just as checking your programs. So the type theory or the logic that backs the COC proof assistant is indeed called the calculus of inductive. This is in fact an into simply type lambda calculus with a bunch of constructions, bunch of things like type operators, dependent types, polymorphic types, inductive data types, some restricted form of general recursion, so on and so forth. So it is in fact a constructive logic or constructive type theory, which means that to start with, it doesn't really assume any sort of classical axioms like law of excluded middle or any kind of equivalent. But of course, if you want to do classical mathematics in such kind of proof assistance, you could go ahead and import classical axioms with a piece in mind, because it's provably safe to have calculus of inductive constructions plus law of excluded middle, for instance. you won't be able to prove false. It's probably safe. So I think another kind of important feature to discuss here is, in fact, the organization of the universes. So in such kind of proof assistance, you have, you just need to organize universes one way or the other, and the way Coq takes it is as follows. So you have three different sorts of universes, namely prop, set, and type. Prop is in fact the universe of propositions. It's impredicative, in which computational abilities are kind of restricted, because in an impredicative universe, if you allow computational abilities together with the assumption of law of excluded middle, then you can easily prove false, and this will basically make your proof system inconsistent, and this is something you want to avoid, right? So luckily enough, we have an alternative called set, in which, I mean, you can basically do computations and assume any sort of any form of law of excluded middle, but it is a predicative universe. And the third sort of universe is called type, which is the universe of both sorts, namely prop and set, and it's basically presented in a cumulative and hierarchical manner. Namely, it's basically given within a stratification. So, of course, to avoid Russell-like or Burali-Forti-like paradoxes. So more or less, I mean, the technical introduction to Coq is kind of something like this. Once again, it's basically an environment which allows you to program proofs just as you program your functions. So, well, I think it would be pretty inappropriate if I make an attempt to explain category theory in front of mathematicians. It would be a bit of a shame, but anyways, but nevertheless, I would suffice to say that, category theory is in fact providing some sort of structural foundations to do mathematics, alternating especially axiomatic set theories. Well, in that sense, a category is just nothing but a structure or just collection of objects and arrows, such that for every single object you have the identity arrow, and you have composition operation defined over arrows, which must be associative, and the identities disappear within the composition. So the structural nature of category theory makes it very suitable to be implemented in proof assistance like Coq. And of course, there are a bunch of existing libraries out there implementing categorical objects within Coq. So I just wanted to list 5 of them here, including that of mine. Some of them are standing with papers, some of them do not. So for the equal and the homogeneous treatment, I just wanted to provide the GitHub links to the source codes if you are interested in any sort of development and implementation or kind of like objects. Of course, you can navigate through the links and play with them. So a few words indeed on the design principles. So in general, if you want to computerize any sort of mathematical framework, maybe the first thing that you need to do is go ahead and formalize mathematical objects within the provided programming language, and that's what we do here indeed. So when it comes to formalizing categorical objects, we are basically employing Coq type classes together with the use of dependent or indexed data types. So I think more or less, I think all of the other existing libraries are basically embarking on the same approach in that sense, modulo tiny little changes. So here, what you monitor is in fact an example. It is in fact categorical functors implemented as a Coq type class. Well, as a side information, a functor is in fact an arrow in between categories, mapping arrows and objects, preserving the identities and composition. So here in this implementation, the field called fObject is basically responsible for mapping objects, and fmap is basically mapping arrows. And these two fields are indeed that they are called proof obligations, and they are there to make sure that the identities and the composition is kind of preserved. So as for the use of dependent types here, well, if it applies, I think it becomes much more apparent within the implementation of the field fmap here. So let me go through an example. So suppose we are given a pair of, we have an arbitrarily given category C and D, and the functor, let's say G, defined from the category C to D. And of course, this functor is going to map every single arrow from A to B in the category C into an arrow from fObject of G of A to fObject of G of B. Well, of course, the type of fObject is completely depending on the functor instance itself. It's an indexed data type. So it's something not surprising. It's indeed, it's a prize. That's something what we want to obtain at the end of the day. But we have to admit that, I mean, on one side, employing, dependent types when it comes to implementing or let's say defining mathematical objects, of course, it brings in some sort of high level of expressiveness. But on the other hand, it's a little bit too cumbersome when it comes to proving properties of dependently typed instances. So what I mean, maybe, so I can basically clarify the point further with this example here. Suppose we are given a pair of functors, f and g, defined from some category C to D, and the goal is to prove that f is g. And the sameness measure here is, in fact, the constructive or the Leibniz equality of type theory, which is constructed through the reflexivity construction. So to prove that two functors are in fact the same, all you need to do is to demonstrate a sub-goals that they basically map objects and arrows in the same fashion. Yeah? So here's the first sub-goal to the main lemma. F and G are basically mapping objects in the same fashion. So of course you can go ahead and state this proposition and try to make an attempt. Make an attempt to prove it, because the type checks. I mean, the type of F object of F is indeed the type of F object of G. So of course, depending on the definitions of F and G, you can immediately make an attempt to prove this proposition. But the same thing is not valid, unfortunately, for the case of F-map. I mean, when it comes to map arrows, because F-map F, the equality in between F-map F and F-map G cannot be directly stated because it doesn't type check. These two guys are of different types. So the type of F-map F is basically represented by the expression down here, and the type of F-map G is the one below. So of course they are different. So what we are trying to do is indeed to compare objects of different types. That is indeed purely illogical. So so the first thing to do is in fact to go ahead and prove that these two guys are of the same type, maybe their types unify, and only then we can make an attempt to prove whether F and G are mapping arrows in the same fashion. So so this problem is in fact not easy to solve because it boils down to, or let's say reduces to the problem of dependent pattern matching, or let's say higher order unification, which is in general undecidable. So we have no solution. But fortunately, of course, for some particular cases, of course, depending on the definitions of F and G, we could make an attempt to prove this. And so why do we have such a problem? I mean, of course, the problem originates from the fact that, the contextual equality of category theory is not 100% reflected is not 100% represented by the constructive equality of type theory. So there is a mismatch and there's a gap, and it's impossible to close this gap in general. But of course, as I said, what we could do is we take particular cases and try to solve this problem for that specific case. Suppose one way or the other, we manage to indeed prove that F and G are basically mapping arrows and objects in the same fashion. Are we done? Not yet. We still need to prove that indeed their proof obligations are the same. So it's a bit strange. So we are trying to make an attempt to prove that different propositions, different proofs of the same proposition are the same. Of course, again, this originates from the mismatch in between the contextual equality of category theory and structural equality of type theory. And of course, we just need to employ a proof irrelevance axiom to get this solved. Okay, so the coverage of the library, I mean, I think I've been implementing lots of things ranging from categories to monad algebras, Eilenberg-Moore structures and all that constructions and lots of theorems. But so as I've been mentioning earlier, so all the other existing libraries are more or less embarking on the same sort of design principles. So the novelties are in fact due to non-existent and different implementations. So in that sense, I think I managed to implement lots of novel things, especially in terms of adjunctions. So so I have two different definitions of adjunctions with a proof, with an equivalence proof of them. One definition is suitable for some proofs, the other for some other proofs, well, within a proof, you may want to switch between definitions, and of course, this will allow you to do so. And the universal property of adjunctions is something that I also managed to prove, different than the other existing libraries out there. This one is interesting. So the fact that the internal language of the category induced by any Cartesian closed preorder is in fact the language of intuitionistic propositional logic. Maybe it's too easy to be proven, so none of the other libraries are just including this. Comparison theorem for the Kleist deconstruction that even gave me a paper a couple of years ago. Now I'm struggling with the same sort of theorem, but this time for the Eilenberg-Moore structures, which requires lots of functional equalities indeed. So let me just spend a couple of minutes also on the case study, in which I'm planning to demonstrate you the fact that, you know, the soundness, I mean, the intuitionistic propositional logic is sound with respect to categories induced by any Cartesian closed preorder. So, well, a preorder is nothing, you know, but a set enriched with a binary relation which must be reflexive and transitive, and every preorder induces a category with the following fact. So the objects of the category are indeed the members of the preorder itself, and as for Dyarovs, we define them as follows. So if for every pair of members in the preorder, if they are related by the underlying relation, then this relation is reflected as an arrow in the corresponding induced category. Of course, you have enriched preorders. You know, a preorder is called Cartesian closed if it has the greatest element, binary meets, and the Heyting implications. Well, these structures are correspondences of some other structures by the category theory side. The greatest element is in fact the terminal object. You know, the binary meets are indeed products, and the Heyting implications are just exponentials. So this is one leg of the interpretation. In the other leg, of course, we have intuitionistic proposition logic, which is presented in this very tiny little and easy syntax. So you have propositional identifiers, the ground propositions, the truth value. You don't have falsity because it's a constructive logic in which you are not allowed to prove false. So as for the logical operators, you have conjunction and implication, and every single proposition is indeed either valid or invalid under some context, which are represented by list of propositions, if you want. I mean, so implementation in Coq is not really a big deal, just one-to-one correspondence. We benefit inductive types of Coq, and for every single constructor here, we have a unique constructor. There's nothing to discuss here, and the contexts are represented by list of propositions indeed. So, of course, well, this syntax is being governed by a set of rules. Well, we have 9 rules for this fragment of the logic, each of which are really simple, but maybe focus on this one. It's familiar to everybody, I think. It's called modus ponens. If you have phi implies psi, and phi at the same time under the same context, of course, you can go ahead and deduce psi. Yeah. So we also need to implement these rules within the proof assistant for the sake of completeness and implementation. So, well, again, we are benefiting from the Coq inductive types. So the implementation given here on the slides and this one in Coq's syntax, they are in one-to-one match with a single different set, of course. I mean, so this one is named axiom 1. This rule is named axiom 1. This is axiom 2, axiom 3, 4, and so on and so forth. So because you have some naming restrictions within such kind of environments. So here is the maybe the most important point, the interpretation function that's defined from the intuitionistic proposition logic into categories induced by any Cartesian closed preorder. So the function is basically, so every single proposition is represented by a distinguished object in the category. The truth is represented or interpreted by the terminal object, the propositional end by categorical products, implication by categorical exponentials. These 2 lines are in fact referring to the interpretation of the context. So empty context is by the terminal object, and the non-empty context is basically categorical products of the interpretations of every single individual proposition. So implementing this in Coq is, of course, is a bit too cumbersome, is a bit hard to parse for human eyes, but I think it's not really a big deal. It's just the same thing. So the interpretation function is called M here, defined from IPL to the underlying category. Every single proposition has a corresponding object, distinguished object. Here you see the interpretation of the truth value as the terminal object, the conjunction as product object, implication as exponential object, and these 2 lines are referring to the interpretations of the contexts. Then you can go ahead and state the main statement, the soundness proof. So if under the context gamma, some proposition phi is provable within the scope of IPL, intuitionistic propositional logic, then there is a map in the, in any sort of category induced by Cartesian closed preorder from the interpretation of gamma, the context to the interpretation of phi. Okay, here is the sound statement implemented, well, just in Coq. So this is a link. If you're interested, you can just click on and navigate through the corresponding proof. So of course, I'm not going to dig into the proof details, but it's the proof proceeds by a structural induction on the structure of rules. So we have 9 cases because we have 9 rules, and it's just a structural proof, and it's implemented and checked by the proof assistant Coq. If you're interested, once again, of course, we can refer to the library. So maybe a few words on what's next. I think I'm a bit above the time here. I'm basically trying to center my category theory library around the functor equalities, this problem, which is undecidable to start with, but of course, for particular cases, why not to make an attempt to solve this problem. So in terms of the functor equalities, I think these three theorems are really relevant. So comparison theorem for the Eilenberg-Moore construction requires at least a couple of functor equalities. Beck's monodicity theorem is also another interesting one, maybe a case study for a graduate student would be, to prove that category of categories is Cartesian closed. And again, it requires some sort of, a basic form of this problem. And on the other side, I'm also interested in interpreting programming language constructs in the category theory in terms of categorical structures. So one of the interesting points is indeed to interpret dependent products in terms of adjunctions and try to prove some properties benefiting from the universal property of adjunctions. And of course, sky is the limit, and there are lots of things remaining out there to be implemented in such kind of proof assistance. Okay, that concludes what I wanted to say. Thanks a lot for your time, and if you have questions, of course, I will happily get them.
I would like to thank you, Professor Ekici, for his valuable presentation. Is there any question or comment to Professor Ekici? It seems there is no question. Thank you again for your presentation.